Okay, get ready for something that sounds like it's straight out of science fiction, but is 100% real. We're going to look at how it's actually possible for water to do two completely opposite things at the very same time. So let's just put the question right out there. How in the world can water boil and freeze simultaneously? I mean, that just sounds wrong, doesn't it? It feels like a total contradiction.
And everything we know from our daily lives tells us this should be impossible, right? At sea level, water freezes down here at 0 degrees Celsius, and it boils way up at 100 degrees Celsius. There's this huge 100-degree gap between them. So how could they possibly overlap?
Well, to solve this little puzzle, we have to look past just temperature. Turns out there's a secret ingredient at play here, something we almost never think about. The reason this whole thing feels so counterintuitive is because our everyday world is missing one crucial piece of the puzzle. And that piece? It's pressure. Yep, good old-fashioned pressure. It's the variable we usually ignore, and it completely changes the rules of the game. Think about it like this. Here at sea level, you've got the entire atmosphere pressing down. So for water to boil, it needs a ton of energy to push back. It has to get 200 degrees. But if you climb a mountain, the pressure is lower, right? The water molecules can escape way more easily, so it boils at a lower temperature, maybe around 90 degrees. So, what if you take that to the extreme? What if you just keep lowering the pressure, pulling almost all the air out into a near vacuum? Well, that boiling point just plummets, and it gets shockingly close to 0 degrees.
So you might be wondering, how do scientists even keep track of all this? How do they know what water will do under all these different conditions? Well, they have this amazing tool, and it's basically a map for water. It's called a phase diagram. And just like a regular map, it has axes, one for temperature and one for pressure. And this chart tells you exactly where you'll find water as a solid, a liquid, or a gas. It's like a cheat sheet for the states of matter. And on this map, you can see the borders between the different states. You've got the line between liquid and gas, that's the boiling point, and the line between solid and liquid, that's the freezing point. But the really wild part, all three of these borders come together and meet at one single, incredibly precise spot. In that special intersection, that one and only place where solid, liquid, and gas can all exist at the same time in perfect harmony, that's what scientists call the triple point. So what are the exact coordinates for this magical spot on the map? Well, the temperature is 0.01 degrees Celsius. Okay, so that's basically freezing, just a tiny, tiny fraction of a degree warmer than what we're used to. The pressure, though? Oh, that's where things get really extreme. It's about 611 pascals. Now, I know that number probably doesn't mean much to you, so let's put it in context.
The normal air pressure we're sitting in right now is over 100,000 pascals. The triple point is at just over 600. That is less than 1% of normal atmospheric pressure. And that is why you never ever see this happen in your kitchen. The conditions are just incredibly extreme.
Okay, so the theory is cool, the map makes sense, but what does this actually look like in real life? Let's walk through how this goes down in a lab.
All right, picture this. You take some water that's already really cold, almost freezing, and you put it in a sealed glass chamber. Then you hook up a vacuum pump and start pulling all the air out. As that pressure plummets, something amazing happens. The water starts to boil, even though it's still cold. But here's the kicker. That boiling, that evaporation, it takes energy, and it steals that energy in the form of heat from the water that's left behind. This is called evaporative cooling. It's so intense that the water gets colder and colder until, bam, it hits its own freezing point. And that's the moment of truth. You literally see bubbles of vapor rising from the liquid while a delicate layer of ice forms right on the surface, boiling and freezing, side by side.
Okay, I know what you might be thinking. That's a neat party trick, but who cares? Well, it turns out this weird little point in physics is actually incredibly important, with some really serious, real-world applications. For starters, it's the gold standard for measurement. The triple point is so stable and perfectly repeatable that for over 60 years it was literally the official definition for the Kelvin, the scientific unit of temperature. It's also the magic behind freeze-drying, that instant coffee or astronaut ice cream. By dropping the pressure way down, you can make ice turn straight into vapor, which is the perfect way to dry out delicate things like food or medicines. And get this, it's even used in space exploration. The pressure at water's triple point was used to define sea level on Mars, because the Martian atmosphere just happens to hover right around that same super low pressure.
So yeah,
The big takeaway here is that this isn't just some weird quirk of nature. It's a fundamental anchor of physical science. It's a constant we can rely on for everything from calibrating our most sensitive instruments to making food that can survive in space.
So let's just take a second to wrap this up with a thought that I think really captures the beauty of all this. I just love that description. It's the one unique point in the universe of temperature and pressure where water gets to be all three of itself: solid, liquid, and gas, all at once, in a perfect dynamic balance. And that leaves us with a pretty fascinating question. We've seen that water can be a solid, a liquid, and a gas all at the same time. But honestly, that's just scratching the surface. At extreme pressures, scientists have confirmed over 19 different kinds of ice. It just makes you wonder, what other incredible secrets is this very familiar molecule still hiding from us?